I wanted to start today by sort of giving an overview of what we currently know and where we're going in the next couple of weeks. The first part of this course is dedicated to really getting a lot better at integration. And sometimes it feels very intimidating, and you feel like there's a lot of new stuff that you've never seen before and it's crazy, but I want to sort of give you some context. And you might see that, okay, it's not so much that there's a lot of new stuff, it's just that we're strengthening our old skill set. So from Calc 1, we learned a couple of things. We learned 10 basic antiderivatives, and these are things like what's the integral of e to the x, the integral of 1 over 1 plus x squared, the integral of secant, that's sort of the strangest one, log secant plus tangent. We said, well, if it's not one of these, let's use some algebra or some trig identities to rewrite it. And maybe that'll help. And if that didn't work, we had substitution. And this is sort of the fundamental theorem side of integration. Now, there are other things that you can put into play when you're talking about integration, particularly if you're talking about definite integrals. You might have geometry. And for the most part, that was, oh, it's a circle. And that's mostly going to be true for what we do in calculus. If we're going to make an appeal to geometry, it's because there's something like a circle. In Calc 3, we'll say, oh, it's a sphere. We know a little bit about spheres. There's also symmetry. Symmetry here being things which are odd. Odd functions were great to integrate. And then we said, well, if nothing else, we can approximate it. And that's what Riemann sums were. Riemann sums are sort of the idea of let's break things up into rectangles, and then let's figure out what's going on. So that's what we knew at the end of last class. In other words, last semester. So where are we going? Well, between us and our next exam, we're going to more or less cover 6 topics. So here we go. I want to show you where these fit in. The first topic, which is today, is we're going to add a new piece here. So this is the big thing. We're going to call it integration by parts. And we'll talk more about what that means. Essentially, I guess I'll spoil it a little bit. How do we handle things which involve multiplication? And so that's integration by parts. The next thing we're going to talk about are integrals involving trigonometric functions. That's our next topic. What that is we're coming up here, and we're just going to bolster our knowledge and our use of trig identities to help us rewrite functions. So really, when we talk about trigonometric integrals, it's like, let's work on our trig identities and do a little bit of substitution, but pretty straightforward substitution. The next thing after that is something called partial fractions. Now, you might think partial fractions is a really complicated calculus technique if you've seen it before, and if you haven't, you might now think it is. But actually, partial fractions is nothing about calculus. Partial fractions is algebra. So what we're going to learn is a little bit of algebra that will help us do certain integrals. So in other words, we're taking our skills and we're just sort of strengthening them up. All right, now I said there were a few more. Now comes the really fun one. And I think it falls into here. And that is trig substitution. But trig substitution, I think you should notice there's a word, substitution. So it's really about using substitution in a smart way. And we're going to show how we can do that. Now the last 2 topics, well, one of them says, you know this Riemann sums, we can do better. So we're going to talk about better ways to do approximation. So we're going to call that numerical integration. So we're going to beef that up and get a little bit stronger there. And the very last topic, it doesn't really fit into a box. So we'll put it in sort of an amorphous cloud here. And what this is improper integrals. Now, basically, when we say the word improper, we mean something involves infinity. So how do we handle it when there's infinity involved? So that's where we're going. Now, I want to point out something really important here, which is this box in the corner, your 10 basic antiderivatives, has not changed. We're not going to be adding a whole bunch of new antiderivatives. So the things that you knew at the end of Calculus 1, as far as antiderivatives, that's as far as we're going to get. Really what we're going to be learning is learning about how to rewrite integrals and how to change them. Our real goal is to say, we only have 10 things we can do antiderivatives of. So let's figure out how to make things simple enough so we can get down to one of those 10 things. And then life is good. All right, so let's start with today. So, well, we already know where we're going. It's integration by parts. And the way we sort of motivate it is to remember, where does the rules for integration come from? The answer is they come from rules for derivatives, because derivatives and integrals are two sides of a coin. And we've already seen some of the rules. The first rule that's listed here is that derivatives are linear. So integrals are linear. We also have the chain rule. That became substitution. And the other big rule for differentiation is the product rule. So what do we do when we have a product of two functions? And so if I have the derivative of f times g, it's f prime times g plus f times g prime. And what does the rule become? That's what we're going to talk about right now. All right. So, here we go. We're going to start with our product rule. So there's our product rule. And we take the antiderivative of both sides. That's not so bad. Now when you take an antiderivative of a derivative, you get back to where you started. Well, basically. More to come on that. So what we have is that f of x times g of x is the antiderivative of f prime times g plus the antiderivative of f times g prime. Now we rearrange and we get the following. The antiderivative, or if you like, the integral of f of x times g prime of x dx is equal to f of x g of x minus the integral of f prime of x times g of x dx. Now there's another way to write this. So oftentimes what people do is we'll say, well, we're going to call this thing f of x, we'll call that u. And so then du would be f prime of x dx. And g of x, we'll call that v. So then dv would be g prime of x dx. So oftentimes it's rewritten in the following form. The integral of u dv is u times v minus the integral of v du. I've written it down for indefinite integrals. Same process works for definite integrals. So you can do integration by parts for definite integrals, and you can do it for indefinite integrals. It's all good, all good. Now you might think, have we really accomplished anything? Because looking at what we have here is we're starting out with an integral, and we're saying, hey, something that involves an integral is equal to something else which involves an integral. It doesn't feel like we've made a lot of progress. But the hope is if we choose our pieces well, that our new integral is somehow easier to perform. So, this is what we have. We've essentially transformed one integral into a new integral. Now we have to figure out how to do it, because some choices will get us closer to an answer, and other choices will take us further from it. So how do we make a good choice? Well, notice what we do. On one of our pieces, say our u piece, we're going to differentiate it. And on the other piece, we're going to integrate it. So if I have a piece which is really hard to integrate, but has a beautiful derivative, that's a good choice to be the part where we take the derivative of it. So we can make it u. Another case, and this shows up often, is if you have like x to a power. See, because if you have x to a power, if you were to keep taking derivatives, eventually it goes away. Now I should say, when I say x to the power, x to a whole number, like x cubed or x to the fifth. not something like x to the 3/2. I want something where as I keep taking integration by parts, it just goes away, goes to 0. On the other hand, if I think about the dv part, well, that's the thing I integrate. Well, I want something that's easy to integrate, because I have to integrate. I want something, perhaps, which is, I put here, stable. And by that I mean something that, look, it doesn't really matter if you integrate it, it's going to be the same thing. So that's something that's really nice to work with. E to the x is the classic example. Sine and cosine are also similar to that. If you integrate sine, you get negative cosine. You integrate cosine, you get positive sine. So more or less they stay the same. They're not changing, so they're really good candidates. Now, there's a note here. 1 dx might be an option. Now you might say, what does that mean? So let's do a quick example here. So do it right here. So suppose you had the following. We've talked about this function before, log of x, but we've never actually talked about the antiderivative of log of x. Now, I claim we don't know the answer yet. Well, that's easy because we don't. But I also claim we can find it with our new tool. But the thing is that when you look at this integral of log of x, your natural reaction is integration by parts should not apply. The reason I say that's the natural reaction is because if you're doing integration by parts, you really have a product of two things here. How many things do we see? We see one thing. So here's the fun, subtle thing. It turns out, true story, that log of x is the same as log of x times 1. Now, we have two things. All right. So what happens next? Well, we need to decide which part do we integrate and which part do we differentiate. Well, we know we're not going to integrate the log of x part. The reason is, if we knew how to integrate the log of x part, we wouldn't have even bothered. So we need to make that the part that we differentiate. So in other words, this part needs to be the u, which means everything else is the dv. So we know that u equals log of x. So we say, what's the derivative of u? Well, what's the derivative of log? 1 over x. Now notice, there's a sort of a technical term for this. We call this nice. And it's a nice derivative. So that's good to know. Now, we also have that dv is 1 dx. So what's the antiderivative of 1? X. So we have the integral u dv. So according to the rules, u dv becomes u times v. So log of x times x minus the integral of v du. So x times 1 over x dx. Well, x times 1 over x, can we do anything to integrate that? Now you might think, maybe we should do parts again. Or maybe we can do algebra. See, like the x's cancel? Cool, good times. All right, so now it becomes, well, what's the integral of dx? It's x. So the first part, I'll put the x in front, x log x minus x, and because we want full points, plus c. So there's our antiderivative of natural log of x. Now, could you memorize this? You could if you wanted to. But for me, I think it's just as fast to remember the product rule, because I find 10 things is already a lot of things to remember. So I don't want to try to memorize 1,000 things. So, all right, so there's the integral of log x. So notice you added a 1. Now, you won't do this very often. Log of x is a good example. Any other guesses on another time we need to do it? Think of your favorite function. Yeah, arctan. Yeah, that's a good function. That's a really good function. All right. Now, there's a piece of advice here at the bottom, and I think it's worth repeating. If in doubt, try something. Now, if it doesn't work, try something else. but never give up until the exam is over. All right. But really, don't just stare at a piece of paper and be like, I don't know what to do. If you don't know what to do, try something. Now, don't try to make some creative new algebra. Avoid that. But say, well, what if I tried this? And let me see what that does. Well, that didn't work. Okay, let me try something else. It's amazing how if you just try something, you oftentimes find you can make a little bit of progress. All right, let's try some more examples. All right. What is the integral of x e to the x dx? We want to find that. Okay. So, first off, what technique should we use? Yeah, integration by parts, right? Because we're talking about integration by parts, so of course we should do it. But let's think about how we would sort of see integration by parts. When we think of integration by parts, what is it we're looking for? We're really looking for products, right? Because the way that integration by parts came from was a product rule. It's like, oh, I have two things multiplying together, and maybe if I manipulate it through integration by parts, I can get it to a simpler integral. Now, I have to decide which part should be the u, which part should be the dv. So which part should we differentiate? So our two parts are essentially the x and the e to the x. So we think about e to the x. Does it matter if we integrate it or differentiate it? No, it doesn't matter, right? Because whichever choice we do, we're going to end up back at e to the x. Now let's think about x. Does it matter if we integrate or differentiate? It does matter in the sense that we're going to get different things. If we integrate, we'd get to x squared. If we differentiate, we'd get to 1. Now, between the two of those, which one would we probably want to work with? We'd probably want to work with 1, because that sounds simpler. So that tells us that the x part, this is going to be the part we differentiate. So that's our u. The e to the x would be our dv, because that's going to be the part we integrate. So we have, I'll put it here on the side, u equals x, which means that du is dx. dv would be e to the x dx, which means that v is e to the x. All right, so according to the rule, we're going to get the we're going to get uv x e to the x minus the integral of v du. So e to the x dx. So uv minus v du. Do we know the integral of e to the x? Yeah, it's e to the x. So x e to the x minus e to the x. And for full credit, plus c. Yeah. And that's the answer. That's not so bad. This integration by parts is kind of fun. Well, let's try another one. Integral of x e to the x squared dx. All right, now, what should be our u and what should be our dv? Of course, that's a misleading question. What should we do here? Someone said substitution. Is there a good substitution to make here? If we substitute x squared, right, u equals x squared, what would du be? 2x dx, right? Yeah, so we can take the 2 across as 1/2. So this will become the integral of 1/2, because of this x dx becomes 1/2 du. And the e to the x squared becomes e to the u, which becomes what? Yeah, 1/2 e to the u. Of course, plus c, and then we're not done. What's left? Yeah, go back. 1/2 e to the x squared plus c. All right. Now, you might say, Steve, today was a parts day. Why are you throwing in a substitution? See, the thing is, parts is like our shiny new toy. And we're like, wow, this is shiny. It's very exciting. And you're always tempted, like, once you have something new, to always use it on everything, but it doesn't always apply. In some cases, there are other things that work better. So there's a warning here. Just because you have a new tool, don't forget your old tools. The old tools are really good, especially substitution. Substitution should always be the very first thing you're looking for if it's not something which you can automatically integrate. We're going to talk about various tools. We already went over at the very beginning that we have more tools coming. But here are some things that we already know. Look for your algebra, look for trig identities, look for substitution. Product rule, I don't want to say it's the last resort, but it should definitely not be the first thing you jump to. You should sort of do a scan. All right, let's try another one. And hopefully there's enough space to do this one. Integral x to the fifth e to the x cubed dx. Can we integrate that? What can we do? Is there anything we can try? Remember, what's our goal? Our goal when we're faced with an integral is to say, is there something that I can do to simplify it? Even if I can't integrate it right away, can I simplify it and make it something easier to work with? If you see something we can try. Somebody says substitution. What's a good substitution for us to try to make things simpler? X to the third. That's a really great substitution, right? Because what do you see? You see x to the third is inside of this function e. And oftentimes when you see a function in a function, that's a sign to think of substitution. So I'm going to, just so I don't confuse myself too much, let's let t, because I can choose any symbol I want, be x to the third. The reason I want to avoid u is because u and v might show up in a minute if we do integration by parts. What would dt be? 3x squared, right? Yeah, and then we throw on a dx. The 3, that's a constant, that's easy to move around. I'll just move to the other side. Now you'll notice that does not match x to the fifth. So does that mean we have a bad substitution? No. What can you do with x to the fifth? Break it up as? Yeah, so we can think of this as, I'll think of this as x cubed, e to the x cubed, times x squared dx. So the x cubed and the x squared are the x to the fifth. And I move this x squared to the end because that's going to be replaced. So we now have that. If we do our substitution, this becomes t, e to the t, and then there's a 1/3 in front, dt. Okay, now what do we do? Well, we could do integration by parts, so we could say, wait, we already did it. So let's not do more work. Let's use our existing work. Because, mathematicians, we like to recycle. All right. So according to the formula, essentially all I'm doing is instead of x, I have t. So there's a 1/3 in front. I'm not going to forget about that. Then I have t, e to the t, minus e to the t. And I always like to put the plus c on the very end. Are we done? No. What's left? Yeah, you've got to get the x cubed. Because you started with x, so you have to end with x. This is an indefinite integral. So 1/3, then it'll be x cubed, e to the x cubed, minus e to the x cubed, and then plus c. And that's our answer. Good. Good. All right. So let's do something a little different. That was indefinite integral. Now we'll do definite integral. Now with definite integral, you really have two choices to make. So one option you have, and it's perfectly valid, is to say, look, I'm going to just treat it as if it were an indefinite integral, find the antiderivative, then at the end I do the evaluation. The other option is to do the evaluation as you go forward. I'm not going to claim that one is better than the other. It really depends, and on various problems I'll choose one versus the other. The important thing is that you get the right answer. And you do it in a way that's mathematically correct. So whatever you're comfortable with, that's what you should do. All right, so we have this function, well, yeah, it is a function, y times arctangent of y. I'll go ahead and just tell you we're going to be doing integration by parts. Probably not a surprise. Now the question is, which part do we integrate and which part do we differentiate? So we have two parts here, right? Y and arctangent of y. Which part should we integrate? Well, the reason I'm asking which part we should integrate is because we need to know. Okay, so again, which part should we integrate? No, we integrate the y. Why? Because do you know the integral of r? Okay, all right. This is silly humor. All right. We integrate the y because, do you know the antiderivative of arctangent? Not yet. We could figure it out. Because arctangent's hard to integrate, that tells us we probably shouldn't have that be the part that we integrate. So we should have that be the part we differentiate. So we're going to make the arctangent, that will be our u, and the y will be our dv. So it's not always going to be given to you in the order. You know, it's not like, oh, it's always you integrate the first part and you differentiate the second part. Or vice versa. So be careful. Okay, so if u is arctangent of y, and we'll say that dv is y dy. So what's the derivative of arctangent? 1 over 1 plus y squared dy. What's the integral of y dy? 1/2 y squared. All right. Now, somebody at some point might be thinking to themselves, why does he keep suppressing the plus c? And the answer is because these are stepping stones. There's always going to be sort of another integral to do. And we're just keep putting out our plus c until the very end. That's what's happening. All right. So, according to this, we're going to have u times v. So I'll put 1/2 y squared times arctangent of y. And this is a definite integral, so I'm going to evaluate from 0 to 1. Come back and do that in a moment. Then minus the integral of v du. So minus the integral 0 to 1 of 1/2, I'll write as y squared over 1 plus y squared dy. All right. Well, that's not so bad. At least it looks a little bit more palatable. Let's talk about the first one. When you plug 0 into this first expression, what do you get? 0. That's good. When you plug in 1, well, 1/2 times 1 times arctangent of 1. Arctangent of 1, also known as pi over 4, which means that this first piece will become pi over 8, because we have 1/2 times pi over 4. Now, how can we integrate something like y squared over 1 plus y squared? Somebody saw what I was hoping they'd see. Now, we're going to do a little bit more next week about how we handle functions like this. These are called rational functions. Rational function is a fancy way of saying it's a polynomial over a polynomial. And we'll talk about the general technique. But oftentimes the question is, rewrite it in a simpler way. So someone said, hey, you know what? You could just add 1 and subtract 1 upstairs. And you absolutely could, because that's like adding 0. And you're probably also saying, why are we doing that? Well, if I regroup, say put the first y squared plus 1 together, and the last minus 1 by itself, now I think about what I have. Y squared plus 1 over 1 plus y squared, what is that? Yeah, it's 1. So what I have is I'm going to have minus, I'll pull the half out, integral 0 to 1, so it'll be 1. And now I cover the y squared plus 1 up, causing a big shadow here. Then I have minus 1 over 1 plus y squared, so that's minus 1 over 1 plus y squared. All right. So those are both simple integrals, relatively speaking. The integral of 1 will be y, because it's with respect to y. So 1/2 y, because of the 1/2, minus. A lot of people would oftentimes forget, the minus goes all the way through. So plus 1/2 integral of 1 over 1 plus y squared, arctan, yeah. And then, of course, we still have to evaluate. All right. Evaluate from 0 to 1. Okay, so what do we get? We get pi over 8. The nice thing is when you plug in 0, you still get 0, so that's good. Plug in 1, you get minus 1/2 times 1, so that's minus 1/2. Plus 1/2 times arctangent of 1. Well, we've already done that. That's 1/2 times pi fourths, which is pi over 8. Which means we have 2 pi 8s. They combine to give us pi over 4 minus 1 over 2. And that's our answer. Nice. Good. All right. Find the integral of theta cubed, sine of theta, d theta. All right. Well, which part should we differentiate? Which part should we integrate? So the sine, essentially, it doesn't matter whether you integrate or differentiate. Essentially, it's going to be more or less the same thing. It's going to be cosine or negative cosine. What happens to the theta cubed? Well, if we integrate, it becomes like theta to the 4th. If we differentiate, it becomes like theta squared, up to constants. Theta squared sounds better. So the theta cubed should be the part that gets the derivative. The sine of theta d theta, that should be the part where we integrate. So there's our u and our dv. So we get u equals theta cubed. That says du is 3 theta squared. dv is sine theta d theta. What's the integral of sine? Is it positive cosine or negative cosine? Negative cosine, yeah. All right, so this is u times v, so minus theta cubed cosine theta minus the integral of v du. So I forgot my d theta there. There we go. All right, so minus cosine theta, 3 theta squared d theta. Now, the good news here, minus minus, I can just make that a plus. So, what do we do now? How do we integrate cosine theta times 3 theta squared? What? Yeah, we can do parts again. Now you're probably thinking, again? Yeah, you may have to do parts many times. The goal here is always we're trying to simplify. In some sense, we've achieved our goal. Because we started with a theta cubed, we got down to a theta squared. That's simpler. But not simple enough. All right, now the question is, which part should we integrate and which part should we differentiate? Well, let's just ask, which part should we differentiate? Yeah, the 3 theta squared part. Now, here's the thing. You might say, couldn't we change our mind? We could. But if you change your mind and apply integration by parts, having swapped which part you integrate and which part you differentiate, you will exactly cancel with what you just did. Meaning, you will have gone back to where you started and used up half a page. So once you commit, you got to commit all the way. Can't stop halfway. All right, so this will be our u. This will be our dv. So we get that u equals 3 theta squared. Du will be 6 theta d theta. dv is cosine theta d theta. Integral of cosine? Is it positive sine or is it negative sine? Positive sign. All right, so the nice thing is there's a plus here. So we have minus theta cubed cosine theta. That's still there. That hasn't changed. Plus uv, so 3 theta squared sine theta, minus the integral of v du. So minus the integral of sine theta times 6 theta d theta. Okay, now what should we do for this integral? Do it again. Exactly. But notice we're simplifying. We had theta cubed. We got down to theta squared. We're down to theta. Odds are looking pretty good for us. We're going really low. So hopefully one more round might be enough for us to get some daylight. So there's u. Well, we kind of see daylight already. So we get that u equals 6 theta. Du is 6 d theta. And then we have our dv is sine theta d theta. And v is negative cosine theta, because we just did that up here. All right. So we get minus theta cubed cosine theta plus 3 theta squared sine theta. I'm just copying these first two over. Minus, and now I'm going to do something really important. This next step will save many people from losing points. It's called a parenthesis. All right? So when you have a minus sign and you're doing integration by parts, a lot of people forget to put that minus sign all the way through. So when in doubt, throw in a parenthesis so you don't forget. All right, so what do we have? We have uv, so that's 6 theta, then times minus cosine theta, then minus the integral of v du. So minus cosine theta times 6 d theta. We still have an integral left to do. All right, so, but I think that one we might be able to figure out. Theta cubed cosine theta plus 3 theta squared sine theta. Now the minus, okay, goes through. So minus minus makes a plus 6 theta cosine theta. This minus comes through again. That's why I say the parenthesis is important. There is another minus here. So what's the integral of negative cosine theta? Negative sine theta. And then the 6 will just come along. So minus 6 sine theta and plus c. That's it. That's not so bad. It's just be patient. Be patient. And it'll work out. Now, let's try something a little bit different. It is possible to get into a cycle, and then if we rearrange, we can get the answer. So here's an integral which I know we can do. There's actually multitudes of ways that we can do this one, but I want to do this by integration by parts. And I'm going to do this fairly quickly because we have another example coming up which is more important to see. All right, so here we go. I'm going to let this be our u and this be our dv. So we have u equals sine theta. Then du, well, that'd be cosine theta, d theta. Then we have dv is cosine theta, d theta. So v would be sine theta. The antiderivative of cosine is sine. So according to the rule, we say, all right, so remember this is the integral sine theta cosine theta d theta. That's equal to u times v. So sine theta times sine theta minus the integral of v du. So sine theta cosine theta d theta. All right? So far, so good? Yes? All right. Now, I'm going to do this a second time. Okay, so what happened? Well, in the first time, I chose the u was the sine theta, and that eventually ended up becoming the cosine theta. So I'm going to let u now be the cosine theta, and the dv b sine theta. All right? I think we're okay. So if we do that, what's u? Well, u would be, that's what we said what u is. U is cosine theta du. That's what we need to know. That's negative sine. Then we have that dv is sine. And what's the integral of sine? Negative cosine. All right. So we have sine times sine. We can call that sine squared theta minus the integral. Oh, sorry, not the integral. uv. So we have cosine theta minus cosine theta, and parenthesis there, minus the integral v du. So minus the integral minus cosine theta, minus sine theta, running out of space here, d theta. All right? Let's clean that up. What do we see here? Cosine squared, right? With a minus. There's another minus out here. So we have sine squared plus cosine squared. Now, let's count our minus signs here. We have 1, 2, 3, 4. Well, that means we're up to a plus. Sine theta, cosine theta, d theta. Yes? All right. So far, I followed the rules. Yes? Okay. All right. Let's do this next part. Notice this and that. Let's just subtract that from both sides. And if we subtract that from both sides, what do we get? 0 equals sine squared plus cosine squared. Now, does that make you nervous? Yeah, because it's not true, right? What is sine squared plus cosine squared? 1. So we've just shown that 0 equals 1. Okay, now, we can't finish the class like that. We won't. We've got like another example to do. Somewhere we made a mistake. And I want to ask you, where was our mistake? Can you spot it? And I will warn you, it is not an integration by parts mistake. And you're like, but Steve, that's all you did. So how can it not be an integration by parts mistake? All right. Are you ready for the answer? Okay, somebody has spotted the key. This integral is an antiderivative. Remember what's true about antiderivatives. Antiderivatives are not unique, right? Because they're up to that plus c. So what happens is these are not necessarily the same function. They're the same function up to a constant, which happens to be equal to that. So there's a hidden plus c here. So you have to be careful. Okay, so that's, because we're going to do an example in just a second, and I just want to be clear that you're going to at some point say, but where does the plus c come in? And the answer is there's a hidden plus c. These two are not necessarily the same. Okay, now the real example. All right, moral. Yeah, don't forget about constants. All right, integral of e to the ax sine bx dx. And I know we don't have a ton of time, so in the interest of speeding things through, let's just talk about what we're going to do, and then we'll do it really quick. We're going to do integration by parts. That's not a surprise. Now you might say, which part should we integrate and which part should we differentiate? And the answer is, you just pick. Because we have an e and we have sine. And in both cases, they're more or less going to behave like the same thing when you integrate or differentiate. You just have to pick a side. And then, remember, once you pick a side, you're committed. You can't change your mind. All right, so because of that, I'll just let this be, Let's have this part be the part we integrate, because it's oftentimes easier to integrate that. Okay, so there's my u and my dv. You could have chosen the other way. It would work just as well. All right, here we go. So u is sine of bx. U is sine of bx. What is du? Yes, that's right. It's b cosine bx dx. All right. dv is e to the ax. What's the antiderivative of e to the ax? Yeah, good. So this is equal to uv. So that's 1 over a e to the ax sine of bx minus the integral of v du. Notice I have a b and a 1 over a. So I can write a b over a e to the ax cosine of bx. Now at this point you're probably saying, it kind of looks the same thing as we had before. Yeah, good. So we're going to do it again. And remember how I said you have to commit? Here's where it's really important. If you're like, nah, let's switch and maybe we'll have it so that we differentiate e to the ax. No. Terrible idea. Would get you backwards. We don't want to go backwards. We want to go forwards. So we're still going to integrate the e to the ax, and we're still going to differentiate the trig part. So u is cosine of bx. Then the derivative of that is negative b sine of bx dx. And then we have our dv is e to the ax, and our v is 1 over a e to the ax. So what do we have? We have our 1 over a e to the ax sine of bx minus b over a. I can just think of that as a constant. So I'm going to pull that constant out. Okay, so I have a parenthesis, uv, so that's 1 over a e to the ax cosine of bx, yes, uv, minus the integral of v du. So there's a b and a 1 over a, and there's a minus sign, so this will become plus. There's a b over a e to the ax sine of bx. Okay? And there's a dx that you can't see because it's so small. All right. Now, at this point, this becomes 1 over a e to the ax sine of bx. Here, minus b over a squared, because I can multiply the b over a times 1 over a, e to the ax cosine bx minus times b over a is minus b squared over a squared e to the ax sine of bx. Oh, there's integral sine dx. Now, what do you notice about this part? It's where we started, right? But it's not where we started, because what do you notice? There's something different in front. So, what we're going to do is we're going to take this to the other side. But because there's a hidden plus c, what we'll end up with is 1 plus b squared over a squared. Because this minus b squared over a squared, we add b squared over a squared times the integral of e to the ax sine of bx dx. Okay, so we added that to the other side. One of these plus b squared over a squared of those is equal to 1 over a e to the ax sine of bx minus b over a squared e to the ax cosine of bx plus c. And finally, to finish it off, well, 1 plus b squared over a squared is the same as a squared plus b squared over a squared. We just want to move this constant across. And if you move that constant across, you get the final answer. And I will write that down. We get that the integral of e to the ax sine of bx dx is equal to, flip, reciprocal. So 1 over a times that, you'll get an a over a squared plus b squared e to the ax sine of bx. And then again, when you do a reciprocal, you get an a squared here. That's going to cancel with the a squared. So minus b over a squared plus b squared e to the ax cosine of bx. And then the c can absorb the constant. And that's it. That's the antiderivative. So it's integration by parts twice, rearrange, life is good. So let's do a couple more. So here we have the integral of sine and log of t dt. This is a function. Well, of course, most functions are functions. But it's a function which we really don't know how to integrate. And it's a really weird-looking function. So if you're thinking integration by parts, it's not a bad thing to try, because if you have something you can't integrate, you can almost always differentiate. It goes back to the old philosophy that differentiation is so much more easy than integration. So remember, what did we say? Really think of it as sine log t times 1 dt. So then we have our u and our dv. So what will happen? Well, du, derivative of sine, is cosine log t 1 over t, chain rule, dt. Then v, well, that's t. So we get that this will be u times v. So I'm going to write it as t sine log of t, then minus the integral of v to u. Now, see the t and the 1 over t? Those actually cancel out. So you get cosine of log t dt. So we start with the integral of sine log t. We got to the integral of cosine log t. Well, don't know how to do that one either. So let's do the same trick, right? I mean, it's not insanity if it works eventually, right? Because there's this old saying, the definition of insanity is doing the same thing but expecting a different result. Well, it might feel like insanity because it's like, are we getting anywhere? And the answer is, if we're careful, the circle might be broken. See, it's true that we're sort of circling around, but what we want to do is we want to get to a point where when we apply it in our second time, we're going to have something different enough. So what do we have? So we have a minus. I'm going to use a parenthesis here. We have our uv. So I'm going to write that as t cosine log t. Then minus integral v du. But the t and the 1 over t again cancel. So we'll end up with a minus sine log t dt. So once the dust settles, t sine of log t minus t cosine log t, then minus, 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 there's 3 minuses, minus integral sine of log t. You might say, well, wait a second, isn't that where we started? And the answer is not really, because notice in our initial one, here we go, let's print that one. Here we have plus sine log t, there's minus sine log t. So these don't actually cancel, instead they combine. So let's put this across. So if we put this across, we would add sine log t, but remember, these may not quite be the same, they're off by a constant. So we can say that 2 integral sine of log t dt is equal to t sine log t minus t cosine log t, and then plus some constant c, right? Because we added that. So there's already one here. We added another one. That gets us 2 of them. We don't want the 2 because we just want to find just one of them. So final thing is integral of sine of log t dt. That's going to be 1/2 t sine of log t minus 1/2 t cosine log t plus c. Done. Now, you might be saying, this feels really similar to what we just did a few minutes ago. Is it the same thing? And the answer is, it is incredibly similar to what we just did. In fact, we could have skipped all this work if we had made an observation. Let's come back here. We said the integral of e to the ax sine of bx dx is equal to this expression here. So let's start with our problem, namely the integral of sine of log t. And let's make a substitution. So let's let this inside part, we're going to call that x. So I'm going to let x equal natural log of t. Or another way I can write that is that t equals e to the x. So what do we have? We have then that dt is e to the x dx. So this is equal to the integral sine of x times e to the x dx. Now look at it. Other than the order, it's e to the ax sine of bx. So here, this is where we have a and b is 1. So we apply the formula, which comes from doing integration by parts twice. We'll get 1 over 1 squared plus 1 squared, which is 2. So 1/2 e to the x sine x, then minus 1 over 1 squared plus 1 squared, which again is minus 1 over 2, e to the x cosine x, and then plus c. But we can't stop there because we got to go back. So this is 1/2. Now, e to the x. Well, e to the x is t. So that's t sine of x log of t minus 1/2. Again, e to the x is t. And then cosine of x, well, x is log of t, and then plus c. Now, if I had bigger screen, maybe I can make them both fit. You compare, you'll see they're the same answer. Well, of course they're the same answer. We did the problem. So what was happening was when we were doing our integration by parts here, the process of getting into a loop, it was actually the same process that we saw before when we did this integration by parts on this problem. Now, you might wonder, well, is this type of integral important? It turns out, yes, it's very important for certain applications in differential equations and other things that you might see further on. So it's good to be able to do that. All right, well, let's try another problem. So, find the area under the curve y equals x cosine squared of x for 0 less than or equal to x less than or equal to pi over 2. So in case you're wondering, that's where pi over 2 is. So in other words, what's that area right there? Well, we know how to find area. The way you find area is you integrate. So we have that the area is going to be the integral from 0 to pi over 2 of x cosine squared of x dx. All right, so now the question becomes, well, how does one go about finding this integral? This definitely feels like an integration by parts situation because you have a polynomial, in our case x, and trig. So when you see that sort of combination, that suggests integration by parts. Now the problem is you also have not just cosine x, it's cosine squared of x. Because what you'd like to do is whenever you see sort of a polynomial and a e to something or cosine something or sine something, you want to say, well, I want to differentiate that. I want to integrate that. So how does you integrate cosine squared of x? Now the answer probably won't surprise you. It is, we don't integrate cosine squared of x because that's not one of our basic functions. Instead, we use trig. So here's a cool fact from trig. And we'll do this a little bit more next time. Cosine squared of x is the same as 1 plus cosine of 2x divided by 2. So this is one of our important trig identities. In fact, there are 6 trig identities that you need to know that'll get you from where you are now, a young mathling, to a seasoned pro. So we will rewrite it. So remember, that's one of our things, is if we don't have a nice integral, look for trig or algebra. Look for things to simplify, because our ultimate goal is always, let's try to make things simpler. And oftentimes, if we make things simple enough, then we're okay. So let's see what we have here.
So this is, I'll think this has two integrals, right? Because I can use the fact that I have this nice plus sign after, of course, we distribute through. So this will be integral from 0 to pi halves of 1/2 x dx. I'm going to think of that as one integral plus integral 0 to pi halves of 1/2 x cosine 2x dx. Now the first integral, that's nice. I like that integral. That's the kind of integral we'd like to bring home to meet our family. Say, family, I've met another lovely function, and I hope you can accept it. All right, what's the integral of 1/2 x? Well, the 1/2, and then of course the integral of x is x squared, and you divide by 2 in front, so another 1/2. And you're going to evaluate from 0 to pi halves. We'll take care of that in a second. The second integral, now it's a lot more simple, right? Because sure, there's a 2, but there's a big difference between cosine squared, don't know how to integrate that, versus cosine of 2x, do know how to integrate that. Now, the u will become the x, because we really want that to become really simple. The dv will be the cosine 2x dx. So let's make we'll put the half with the u. So then du, we'll say it's 1/2 dx. And then the integral of cosine, well, that's sine. But because of the 2, we need another 1/2. So 1/2 sine of 2x. All right, good. So we have uv, so that'll be 1/2 times 1/2, which makes 1/4 x sine of 2x. Evaluate, because it's a definite integral. And then minus integral v du. So 1/2 and 1/2, it'll be 1/4 sine of 2x dx, and then that's going 0 to pi halves. All right, so let's do some work. All right, well, 1/2 times 1/2 times pi halves squared. Well, that's certainly it's a pi squared. Now if you group half, a half, then another half, and another half, that makes pi squared over 16. Next term, well, that's 1/4 x sine 2x, so we'll have 1/4 times pi halves times sine of pi, and sine of pi is 0. Then we're going to subtract 0, right? Because we plug in 0, we get 0. All right. So the next term contributes nothing. That's all right. Sometimes that's how it works out. Then we have minus. Here we have 1/4. The integral of sine, well, the integral of sine would be negative cosine. So negative cosine 2x, but got to compensate for the 2 on the inside. Divide by 2. Evaluate from 0 up to pi halves. Boom, boom. All right. So let's see, what do we get? When you plug in pi halves, well, all right, so we have our pi squared over 16 from the start. Don't forget that. Then we plug in pi halves. Cosine of 2 times pi halves, that's cosine of pi, that's minus 1. So that's minus 1, then times a half times a fourth. So that's minus 1/8. And then, of course, cosine of 0. Well, that's 1. So 1/2 times a fourth is 1/8. But we also have subtract that, so minus 1/8. So we end up with pi squared over 16 minus 1. 16. Why did I write 19? Minus 1 over 4. And that is our answer. Pi squared over 16 minus 1 over 4. Good. Now, sanity check. Is it positive? Well, yeah, pi squared is at least 9, right? Because pi is bigger than 3. 9/16, this is 4/16, so that's a positive number. And, well, seems reasonable. It might even be true. No, it probably is true. Right, we did the math. It checks out. Okay, well, good. That's a lot of practice. We should probably do a little bit of a cool down. So let's try some cool down integrals, just for fun. Okay, so let's try, how about the following? The integral of log of 1 plus x squared divided by x squared dx. Well, now you might think, is this integration by parts? Well, maybe, right? If it were integration by parts, you want to think of it as two things. Now, you can, whenever you see division, you can really think of it as log of 1 plus x squared times 1 over x squared. This is just another way to write it. Now we say, okay, if it were integration by parts, these would be the two parts. It doesn't look like there's a good candidate for substitution, because if you did substitution here, you'd end up with an x, needing an x dx, which you really don't have, and there's no 1 plus x squared downstairs. So we're in our integration by parts, we're doing a cool down, let's try parts. So what would our parts be? Well, I have these two things, and I say, I don't know how to integrate that. All right, well, don't integrate it. So that's going to be the part we differentiate. I do know how to integrate 1 over x squared. Also, that'll be the part we integrate. So, what do we have? Well, we have that du, the derivative of natural log of 1 plus x squared, will be what? Well, 1 over 1 plus x squared, because we're going to take the derivative of log of something, it's over to the inside. Chain rule then says, multiply by the derivative of the inside, so 2x dx. Antiderivative of 1 over x squared, well, that's like x to the minus 2. So the antiderivative will be x to the minus 1 divided by minus 1, which is minus 1 over x. Again, if you're not quite seeing that, what you have is that dv is x to the minus 2 dx, and so what we have is that v is x to the minus 1, and then you divide by minus 1, which means you put a negative in front. All right, so now we're ready, right? So we have our u times v. So this is minus 1 over x, natural log of 1 plus x squared. And then we're going to subtract integral v du. So there's a minus 1 over x times 2x over 1 plus x squared dx. Now, minus makes this plus. I can cancel x with an x. So cancel, cancel. So what do we have? Well, we have minus 1 over x, natural log of 1 plus x squared, plus 2 integral 1 over 1 plus x squared dx. Do we not integrate that? Oh, I hope so. I hope so. Minus 1 over x, natural log 1 plus x squared, plus 2 arctangent of x, and of course, plus c, because it's an indefinite integral. Good, good. Well, I think we have time for maybe one more. So let's try one more. All right. Last one for today. So let's try to find the following. The integral of x secant squared x dx. Now, here's the thing. Much of the time, maybe almost all the time, but I'm not going to say every situation, but most situations, when you do think about integration by parts and you see something that looks like a polynomial, for example, like x, that's going to be the part that you differentiate. So that should be our candidate for you. Now, of course, this will only work is if this part makes sense as saying, is it the derivative of something? Now, hopefully you're getting really comfortable at knowing like, oh, there's a couple of functions which frequently show up as derivatives, and I just know how to recognize them. And secant squared x is on that list. So what we would have is that du would be dx, and the integral of secant squared, I hope we know that, it's tangent. So we'd have uv, so that's x, tangent x, minus the integral of v du. the integral of tangent of x dx. Well, do we know the integral of tangent? Yeah, that's one of those ones that was kind of a weird one. You got to remember it. It's not the weirdest one. So the integral of tangent is log secant. And now plus c. And that's it. And life is good. A wonderful cool down. And we'll pick up again next time when we start delving more into integrals with trigonometric parts, trig identities. Really useful stuff. All right. Hope you have a good day. Bye.